Welcome to class meeting 30 of the Introduction to Optimization. We have two announcements. First one is the homework 7. Actually, it is not available yet from the course homepage, but I will make it available immediately after this class. It's due on the same date as the final exam date. And that is the Wednesday. So when? Next week? Yeah. Next week, Wednesday. And the exam will be placed here at LJ 104, except for two Muslim students who has to obey their religious tradition. You all need to come here at 6:30, and the exam will last for 4 hours. And two students will take from here to here. Got it? So no extensions. No. If you extend, this time interval will also be extended. Okay. Otherwise, it's all up to the TA. Anyway, so these are two announcements. I originally planned to have around 10 homeworks, but it seems we end up with 7. By the way, while we review, I need one correction. So let's see the lecture note of last time. Yeah, here, let me make a copy of this one. Paste. Okay, so this is the page 7 of class meeting 28, and also page 2, page 0 of class meeting 29. And it seems that here, this is okay, but here we have to limit x star as a local minimizer. Otherwise, there is some problem. Okay, so this is the correction. So in the last meeting, we studied this part where we had only one constraint, that is the equality constraint. And here today, we consider the case where we have equality constraint and inequality constraint. By the way, such an optimization problem is called functionally constrained optimization problems. It's general enough, but not completely general. As I told you, the constraint set may not be specified such functions, so be careful. Anyway, I will draw some figures, Venn diagrams today, so you need just to wait. Anyway, the idea is like this. Before, when we studied the duality, the theorems were stated in this way. X star is a primal optimal, and lambda star mu star pair is a dual optimal. And also, we assume strong duality. Then, what happens? This X star and lambda star mu star satisfies the Kkt conditions. That was what we had when we studied the duality, and especially strong duality. But here, the theorems looks different because there is no assumption of strong duality. We just assume that some X star that is feasible to the original optimization problem is a local extremizer sometimes, or a local minimizer in sometimes. So actually, a local minimizer is also a local extremizer. If you want to make everything consistent, you may change this to local minimizer. Still, the result holds. So maybe you want to change this to minimizer. In that case, all 6 theorems shown here starts with the same thing. X star is a local minimizer. X star is a local minimizer. X star is local minimizer. X star is a local minimizer. Slight difference is that strict local minimizers. Got it? So here, the theorem does not assume strong duality and does not talk about dual problem at all. Of course, you know that the nu, or here lambda and nu, may be interpreted as dual variables if you formulate a dual problem. But it does not say anything. And also, the derivations in the chapters 20 and 21 of our fourth edition of the textbook does not link these results with any duality. They just derive this result. Got it? So let's see. So given the equality constraint functions, the first of the necessary condition type result was stated in this way. X is a local minimizer and regular. What does that mean? Regular means that here you are given, for example, m equality constraint functions. And you calculate the gradients of each equality constraint function at x star. And so you have how many? You have m gradient vectors at x star. Regular means that these m gradient vectors are linearly independent. So when you have only a single, for example, this is a scalar valued, what does that mean? The gradient of h at x star is not a zero vector. Got it? So given that local minimizer and that is regular, the result is very interesting. Some vector nu star of length, in this case, same as this number of functions, equality functions. And here the gradient of the objective function is a linear combination of the gradient of equality constraint functions. And this statement can be rewritten in this form. So gradient of f0 plus, what is this? This is a matrix vector multiplication, and it can be interpreted as a linear combination of the columns, where the columns are gradients of each constraint function. So actually, this result is same as this equality. There exists some nu star satisfying this equality. Got it? And you immediately notice that even though this has nothing to do with the duality, and actually this is what? This is what we have seen when we study the duality. This is the fourth condition in the kind of simplified version of the fourth condition in Kkt conditions. So it seems like you formulate the Lagrangian to study duality of the original primal problem. And then you differentiate this Lagrangian with respect to x. Then you have this one. And you evaluate this partial differentiation of the Lagrangian with respect to x, evaluated at x star and nu star, set to 0. That is what? That is this result stated here. So we have just our Kkt condition reappearing here as the result. That's good, because we want to reduce our size of memory, right? So that we can utilize our memory for other purposes. So it's good. And the corresponding result today is this one. Now we have inequality constraint functions and equality constraint functions. And the assumption is that x star is a local minimizer and regular. Here, the definition of regular is a little bit different, and I will tell you what it is. But anyway, the result part is very interesting. This is simply what? You formulate a Lagrangian for this optimization problem, right? And then you differentiate with respect to x, and you evaluate that gradient at x star and lambda star and nu star, and set it to 0. That is this one, right? Of course, here our Lagrange multiplier, lambda star, associated with the inequality constraint function, satisfies what? Here I need to have transpose. Okay. satisfies the complementary slackness. Got it? It is not only non-negative, it also satisfies complementary slackness. So we start with this one today. Got it? So that is the big picture. So first, we make everything simple. So consider minimization of f0 of x subject to f underscore x is less than or equal to 0. So what is this? We remove our equality constraint functions and consider a simple one extreme problem, right? Actually, we already studied the other extreme where we keep the equality constraint functions and remove inequality constraint functions. That is what we studied in chapter 20 of the fourth edition, right? So let's study this one first, and then let's add h of x equals the 0 vector. Got it? So let's examine this one. Now, here goes a definition that the constraint, the set, constraint set actually, or constraint set x in Rn such that f sub I of x star, let me use tilde, okay, tilde. So here, actually, this is what? This is the intersection of the sets of x in Rn such that fi of x is less than or equal to 0, and I from 1 to m, if I remember correctly. No, p. Got it? So this explicit constraint is actually rewritten like this in terms of set operations and set. Got it? Now, each constraint set, right? So I's constraint set is active at x tilde if f sub I of x tilde equals 0. Got it? So see that given the omega explicit and you arbitrarily choose some feasible x, and that feasible x satisfies this one, but some of the functions may equal to 0 at that point, or some of the functions will be less than 0, right? So we call the constraint is active, the inequality constraint is active if equality holds. Therefore, we call the constraint is inactive at x tilde if fi x tilde is, in this case, less than 0. Got it? So active constraint, active inequality constraint means equality holds. In effect, inactive inequality constraint means equality does not hold. Second, let's define the index set I at x tilde as the set of indices such that fi x tilde equals 0. What does that mean? So, for example, you evaluate this inequality constraint function at, for example, 0 vector. That is feasible, for example. And you find that 1, 2, 3, the first 3 functions are active, and last 3 functions when p equals 6 are inactive. In the case, what is this one? This set at all 0 vector equals 1, 2, 3. Got it? This kind of set is usually called the index set, okay? Because it's a set of indices. or in this case subscripts. Now, so this is the index set of active constraints at x tilde. Okay, be careful. Whether the ith inequality constraint function is active or inactive depends on x tilde. If you change the x tilde, some active constraint may become inactive, right? And vice versa. Same here. This index set may change if you find the index set at different x tilde. Feasible. Got it? It's natural. So given that, here goes a very interesting lemma. Now probably you see why we define the activeness and inactiveness of the constraint set, and why we define the index set. This lemma is stated like this. If x star is a local minimizer of this problem, okay, then x star is a local minimizer of this problem. You minimize subject to what? Let me see. Is it true? What does this mean? So let me give you an example. Suppose that our inequality constraint function is simply identity function. So we have such an inequality. Okay. So actually, precisely speaking, minus x is less than or equal to 0 vector, right? So in two-dimensional problem, our omega, the constraint set is this one. Suppose that the domains are the entire R2. Now, suppose x star is a local minimizer of the original problem. Then there are 4 cases. First one is that this is x star, right? And second one is this is x star. Third one is this is x star. And fourth one is this is x star. Am I right? So now let's examine one by one. Suppose the x star is the local minimizer, and like this. In that case, it is a local minimizer without this constraint. Am I right? So here, at this x star, one is the index set, empty set, right? Nothing is active. This is active and that is active. Am I right? Okay, so here, x minus x1 minus x2 is f1 of x, f2 of x. Am I right? Got it? In this case. So, first one is active means that x1 is 0. Second one is active means x2 is 0. But in this x star case, if this is a local minimizer of the original problem, nothing is active. Am I right? So in this case, the index set is gone, So you remove this one. So it becomes unconstrained optimization problem, which means that the entire R2 is the omega. In the case, this is still a local minimizer. Am I right? So, okay. So this case is good. Now, let's see. X1 is 0. Okay. This is not consistent with what I have written. So X star, let me see, 1. This is strange notation. Let's do this. Okay. So let's examine this case. In this case, what is the index set? What is the index set? So x1 is 0. Am I right? Over here. So this is active, and this second function is not active. So modification like this means that you only consider that one. Am I right? Means that you consider the problem here. Am I right? Yeah. Here on the y-axis. If this is a local minimizer, means that any neighborhood, right? In any neighborhood, this is smaller. Then, since this is a local property, removing this is okay, right? So, second case is okay. Now let's consider the third case, and same holes, because we have symmetry here and here. What about this one? In this case, both of the inequalities are active. Means that this is 0 and that is 0. And then what is this one? This constraint set becomes just the set consisting of this only one. And that is also correct. So as you see that if x star is a local minimizer of the original problem, then it is also a local minimizer of this modified problem where only active inequality constraints are included. But now what is this problem? You can rename this one as Hj, right? Then this problem becomes the same as the problem we considered in the last class meeting. The minimization problem with equality constraint functions. So what can you say? So here goes the proposition. If x star is a local minimizer and regular, but here we haven't yet defined the regularity in the constraint optimization problem with only inequality constraint functions. But we know how to define the regularity when we only have equality constraint functions. How do we define? We calculate the gradients of these functions, right, in the index set, and assumed independence. So we define the same way. So here regular means that gradient of fi of x star for all I in the index set at x star are linearly independent. Okay? Then what can we say? We just copy and paste with a slight modification of this first result in the previous page. Right? This first. What is that? Gradient of the objective function is a linear combination of the gradient of the equality constraint functions. But now what? Gradient of active inequality constraint functions at x star. So gradient of f0 x star is a linear combination of gradient of fi x star with I in the index set at x star. Got it? But as I told you, this is a kind of, how to say that, verbal description. So you may say that, then this is same as, the conclusion part is same as there exists lambda star such that gradient of f0 gradient of f0 x star plus summation I lambda star I fi in the index set x star is 0. Right? So instead of using gradient of h sub j evaluated at x star, we only include the gradients of the active constraints like this. But here you may say that there exists lambda star such that lambda star transpose fi x star equals 0. No, I wouldn't say that. Just a second. Yeah. I star is 0 for I not equal to the star, and this one. And you may say that, let me a little bit modify, okay? It's confusing. Gradient of f0 x star plus summation I equals 1 to p lambda I star gradient fi xi star equals 0. Now, are they the same? See that here every I is included. However, due to this first constraint, those not in the index set are removed because this is 0. So this one is same as these two lines. Am I right? And you may say that, okay, but wait a minute. Lambda has been used as one of the Lagrange multipliers such that that is greater than or equal to 0. Where is that condition? Right? So you may wonder. So actually, here goes a theorem. Lambda star is actually greater than or equal to 0. Here. Not just like this. And satisfying what? Satisfies the complementary slackness. Okay. So what can you say? What you can say is that as shown here, if x star is a local minimizer and regular, suppose this condition is not there, so this is not there, so you don't need lambda, but what? It exactly follows this condition. Lambda star is greater than 0, complementary slackness is satisfied, and the gradient is what? Weighted sum, linear combination of gradients of the inequality constraint functions. If it is inactive, lambda is 0, so it's only active ones are involved. Got it? So it's all consistent with what we have been studying. Now, how can we prove? For the proof, we have a figure. This one. So consider this x star. that is feasible, assumed feasible. And here we have, in this example, we have three inequality constraint functions whose level 0 is like this. So this is the, by the way, our textbook uses G instead of, use F instead of F0. So these are the level sets of the objective function. And these G's are actually F's I told you. So this is F1 equals 0. And in this case, we assume that this direction is the F1 is less than, F1 of X is less than 0. Okay? And here this is F2 is 0, and this direction is F2 is less than 0. And this is F3 is 0, and this direction is F3 is less than 0. So our constraint set is this one. And suppose this X star is a local minimizer of our optimization problem. Now, here, which constraint functions are active? F1 and F2. And this F3 can be just ignored to talk about our local property. Am I right? Because locally, around here, this constraint just can be ignored. So this is ignored. Now, this figure is a little bit misleading, so let me redraw and explain. By the way, due to some font replacement, this is the del sign gradient. Okay? So, anyway, let me redraw. So, let me more pointy case. So here this is F1 of X is 0. This is F2 of X is 0. This is F3 of X is 0. Of course, in this case, X is in R2. And let's assume that this is X star we are talking about. Now, this is our explicit constraint. And let's assume that our domain contains this omega explicit. So let's just remove that one. Now, since this area, this part is feasible, here you can draw minus gradient of F1 of X star. Am I right? We've talked about that many times already. Okay? Given a level set, okay, the gradient at here must be what? Must be the normal vector of this tangent plane or tangent line, right? So here, since this is negative direction, so we have omega here. So this is direction of negative gradient of F1. Similarly, this is negative gradient of F2 of X star. Am I right? Now, we claimed that, we assumed that X star is a local minimizer. What does that mean? If we draw a level set here, we may have any level set, right? But what about if we reduce the level? Can it be here? No. If so, we may have to say that this is not a local minimizer, right? So let's say F0 X equals F0 X star. So this is a level set of our objective function, right? Now, if we choose some value smaller than that, that must not cross any part of here, right? So it could like this or like that. So the level set with smaller value than f0 x star must lie from here and there. Okay. Am I right? Or equivalently, you can say that since we assume differentiability of our functions, the gradient vector of the objective function evaluated at x star must lie what? Let me see. Be careful. Let me be careful. Okay, actually, negative. Yeah. So negative should not lie between here to here, which means that positive must lie between here and here, right? Am I right? Is it? So confusing. Okay. Yeah, I do not quite remember. Anyway, the conclusion is like this. We all know that this is a non-negative combination okay. You check it, got it? Because otherwise we cannot end up with our Kkt conditions. Okay, what does this mean? So there exists lambda star greater than or equal to 0 such that okay, so we end up with what we want. And what? And we defined already that lambda I star equal to 0 if the corresponding i's constraint is inactive. So what do we have? We have complementary slackness. So we are done. Am I right? So this is the reason why we again have the same form as we desired. Now, before we move to a general case with equality and inequality constraint functions, there is a very special problem, but important, which we examined just before, is this. We want to minimize objective function subject to x resides in the first ordinate. Got it? So now, let's apply our theorem to this one. So, if x star is a local minimizer and regular. By the way, what does this mean by regular in this case? So as I just told you, this is same as minus x1 minus x2 f1 of x f2 of x is less than or equal to 0, 0. Am I right? So gradient of f1 is what? What is the gradient of f1 function? Gradient of f1 at any x minus 1, 0. Am I right? gradient of f2 at any x, 0, minus 1. So, they are independent. Good. So, every point in the feasible set is regular. That's good. So, let's forget about this. Anyway, it's regular in this problem. Then, there exists lambda star. In this case, lambda 1 star and lambda 2. It's not necessarily two-dimensional. Okay, lambda star greater than or equal to 0, such that first, what? Gradient of f0 x star plus. Let me use the capital D notation. df x star lambda star is 0. By the way, here d of f x star equals the gradient of f1 x star transpose gradient of p of x star transpose. Okay, so the gradients are transposed and placed as each rows. Okay, and so we plug in, then we have gradient of 0 star plus, and we all know what is this one. What is this one? Minus 1, 0, 0, minus 1. Like that. Okay. So minus identity times lambda star, okay, equals 0. I hope I'm right. Yeah, so what is this one? This is same as gradient f0 x star equals lambda star, right? And complementary slackness, lambda star transpose f x star equals 0. What is this in this case? We have something like this, right, in 2D case. So in n-dimensional case, we will have minus x1, minus x2, up to minus xn. So let me see. Something like this. Am I right? Because this is simply minus x, right? Minus x. So if we combine these results, then they can be summarized like this. Let me check. Yeah, gradient of f0 x is greater than or equal to 0 vector, and x star transpose gradient of f0 x star equals 0, and of course x star is greater than or equal to 0. Okay. So here the key is that this is the complementary slackness. So actually we remove the Lagrange multiplier lambda here. Got it? And now let's see what does this mean. So let's go back to our lecture note. No, this one. And there are figures, yeah, like this. So this is the case where x star no inequality constraint is active, right? It's because this first quadrant is our constraint set. In that case, what is this? Does it satisfy three conditions? First, gradient is 0, right? So first condition, gradient is greater than or equal to 0, is satisfied. Second, x transpose gradient is 0. Y gradient is 0. Third, x is in the first quadrant. So this case is okay. Now second, now here this x1 is 0. What does that mean? First, the inequality constraint is active. We've seen something similar today, right? Now here the what about the first one? First one is that here gradient is greater than or equal to 0. What does that mean? This vector here must between here, right? Because each component is greater than or equal to 0. So this is okay. Second condition is that x star, that is this vector, and the inner product of gradient is 0. What does it mean? They are orthogonal. So this angle is right angle. This is a right angle, right? Now here, this is the positive gradient direction. What does that mean? If you move from here to this direction, the objective function value increases, right? So along this line, this is a local minimizer. Okay, it's obvious. And third case is this one, and same as that one. Okay, so gradient is in this area, right? And x star transpose gradient is 0. This is a right angle. And also we have the last case where x star is 0. And here, first condition is that gradient is a positive vector, non-negative vector, so it lies here. And second one is that x transpose gradient is 0. But x star is 0, so inner product with any gradient is 0. So it's satisfied, and x star is, of course, in the first quadrant, including its boundary. Okay, so this case is. Why this is so important? Why this is so important? For example, suppose you have the problem like that. Where is that? Yeah. Problem with such inequality only. Then there are only actually 3 cases. One, the local minimizer is in the interior of the first orthant. Second, it's in the boundary. But if it is a length n vector, how many cases do you need to examine? Actually, to the n, right? Because sum of, for example, 1 of the element is 0, 2 of the elements is 0, 3 of the elements 0, 4 of the n of the elements 0. How many combinations? N choose 0 plus n choose 1 plus n choose 2 plus n choose n, right? So you have 2 to the n cases. That includes what? When the x star is at the origin. Got it? Yeah. So you have exponential cases, but if the dimension is finite and not that large, then actually it may be helpful for you to solve, for you to find x star and lambda star that satisfies these conditions. Got it? So even though I do not carefully examine the examples, you need to work on some examples for your homework. For example, let me give you a problem. Okay, here is the problem. So you want to minimize a quadratic function with a closed term. Subject to x1, x2 lies in the first quadrant, including the boundaries. Now, what you want to do is that you apply the Kkt conditions. Kkt conditions means that x star is primarily feasible. That is this one. lambda star is dual feasible, that is this one. And you have complementary slackness, this one. And the FOMC type thing, this one. Got it? Now, what you want to do is that you want to find x star and, in this case, nu star, but lambda star, satisfying all these cases. How can you find? So the suggestion is this one. Consider the case where, for example, these two are all zeros. And you check whether x equals 0 satisfies all the conditions. So this is okay. That looks okay. And what about that one? So you inspect one by one the cases. Got it? When every element is 0, when only one element is 0, when every element is 0, only one element is 0, two elements are not 0, something like that. Then sometimes you can analytically solve like this. Okay. So here they first try x1 star is 0, which means that x2 star may be 0 or not 0. And then they solve, and they can find, the authors found, have x star and nu star that satisfies the four equations. And also a try means that check the case with x2 is 0. And by the way, in the first case it's invalid because this is -3. In the second case it's valid. Okay? And they also try none of them is 0. But in that case you can show that it's not possible. Okay? It's not that difficult. Okay? So in that way you can find the candidate x star and lambda star. In this case nu star. Got it? Anyway. So we've seen a special case. Another one is, okay, go down, just check, okay. So before we generalize to the problem with equality and inequality constraint functions, let's see some variations. So first variation is this. You minimize f0 x subject to f is greater than or equal to 0 vector. Then in that case, the theorem needs to be modified as what? So then part is changed to what? Suppose you still want to keep lambda is greater than or equal to 0. So there exists such that, then what? Of course you have the complementary slackness. That's okay. But for the first order type thing, what do you do? Is it plus or minus? So I'm asking you, what is the symbol here, plus or minus? Now here we combine our knowledge for the duality. For example, in the minimization, we wanted to find the dual function that serves as a lower bound. So we wanted to subtract something from f0. So here, even though this is in the differentiation form, here is a hidden Lagrange function, Lagrangian, right? There f0 minus something. Because in this case, the problem is minimization, so we want to find a lower bound. But this is what? This is non-negative. And this is non-negative chosen, so we have to subtract. Got it? Now in the second case, suppose we want to maximize f0x subject to f is less than or equal to 0. Then now the theorem, then part of the theorem, suppose we keep still lambda greater than or equal to 0. Then what happens? This Slaney's part is the same always. But now what? Again, we want to find the lower bound and define the Lagrangian dual function. So what? This is negative, this is positive. So we have, be careful, we want to maximize. So we want to maximize the function, so we want to find the upper bound. So we have to add something positive. But here, this is positive, this is negative. So here we must have negatives, minus sign. Got it? So remember the idea we had in defining our Lagrangian and the Lagrange dual function. In the minimization, we wanted to have a lower bound. In the maximization, we wanted to have an upper bound. Got it? And you can fill out here where we want to maximize. So 1, 2. Actually, this is 2 because we examined the first problem. 2, 3, 4. We want to maximize f0x subject to f underscore is greater than or equal to 0. Then the then part, if we keep this lambda greater than or equal to 0, then first complementary Slaney's. And here, what do? We want to maximize some function. We want an upper bound. So we want to add some positive value to this one in defining the Lagrangian. So this is positive, so here the sign is positive. Got it? Sometimes we choose lambda star negative. In that case, this is flipped. If we choose lambda star negative, this is flipped. If we choose lambda star negative, this is also flipped to minus. Got it? So you have the correct Kkt conditions. Now, as I promised, we go back to the general case. So here the problem is the minimization of f0 subject to f underscore is less than or equal to the 0 vector and h underscore is equals to the 0 vector. Now, can we define regularity at x star? Of course. How? We only talk about the inequality constraint functions. And we collect the indices of active constraints. And we take the derivatives of the equality constraint functions. So we compute the gradients of equality constraint functions and active inequality constraint functions. And if they are all linearly independent, we say that the feasible x is what? Regular. Got it? So regularity is easily defined. And the statement is like this. If x star is a local minimizer and regular, then there exists lambda star nu star such that first lambda star is greater than or equal to 0. Second, lambda star transpose f x star equals 0. Third, of course, as we did already, this could be stated here, but anyway, it's okay. But let me write this way. Okay, this is the second one. This is the third one. Because X star is a local minimizer means that it's feasible, so it satisfies the primal constraint. Okay, as we had 4 conditions in the Kkt conditions, right? So this is the first one, primal feasibility. This is the dual feasibility. This is the complementary slackness. And our fourth one is what? Gradient of the objective function at f0 is the summation of the lambda star and gradient of fi x star plus summation of nu j star gradient of hj x star that is equal to 0. Okay. So our Kkt conditions appear again and again and again and again. And of course I'm talking too much about theory, but in the exam in the final exam you will be seeing more of the examples. So it's not like, especially in these chapters 2021 and the chapters I'm going to talk later in today and Wednesday, you will see more of the find optimal solutions or find local minimizers, something like that, not like prove something. Because I'm kind of giving you the results very fast. Anyway, so let me jump to the second order conditions. Of course, I'm not proving them. I'm just introducing those second order conditions. So here, as we formulated our Lagrangian for such problem, we have L of x lambda nu. In this case, this notation is different. Actually, this is the derivative of our original Lagrangian function with respect to x. So I hate that the Chong and Jack's book and Boy's textbook does not have the same notation. But anyway, this is the gradient of the Lagrangian. Got it? So, not gradient, how to say it? This is the D2, the Hessian matrix of our Lagrangian. So we originally have L of x lambda nu, then we differentiate with respect to x, and then we differentiate with respect to x again. Okay. So we have a square matrix. This is a square matrix. This is the Hessian of our objective function. This is the Hessian of the i's, in this case, inequality constraint function. This is the Hessian matrix of J's i's equality constraint function. So we have a square matrix. We utilize that one, and we state the second order conditions. So these are second order conditions. So suppose that x star is a local minimizer of our original constraint minimization problem with equality and inequality constraint functions, and it's regular. Then what? Then there exists lambda star nu star such that for Kkt conditions, those are first order conditions, are satisfied, and then we additionally have this condition satisfied. Here, D square, or you say D2, is what? The Hessian of our original Lagrangian, like this, right? And this function, this matrix evaluated at x star lambda star nu star is what? Positive semi-definite. But I'm not saying positive semi-definite matrix. I'm saying that this function is positive semi-definite on the tangent space, termed like this. Now, what is this tangent space? This is the actually same as this tangent space when we talked about the second order necessary condition. So, as you remember, I hope you still remember, So how did we define the tangent space at x star? So it's like this. So what you do is that you approximate your for example, your first equality constraint function around x star using first order approximation. Then what is this? Am I right? So x equals 0, this constraint set locally is what? Very similar to this one. Why I ignore that one? Because we assume x star is feasible, which means that h1 x star is 0. Okay? So our first order approximation only has this term that is equal to 0. And what is this? If we view this as y, this is what? This is a hyperplane. So now consider approximation of the second one, third one, fourth one. Then how many? We have intersection of hyperplanes, right? Intersection of hyperplanes on which our y can move. Okay? That is the tangent space. Got it? So here, the tangent space for our general constraint optimization problems with equality and inequality constraint functions should be defined as what? In the same way, but now we must involve activeness, the index set of active inequalities, something like this. So here, this is the tangent space. That is the intersection of what? First, and the index set something like this. Okay, got it? So here we have to involve our index set, including all the active constraints indices. Okay, that's the difference. But virtually they are the same. Okay, because the inequality constraints are active or inactive. If inactive, then locally speaking, it can be ignored. That's why we have this result. Okay, so we only involve this equality type constraints. Now this is for the second order necessary condition, and here we have second order sufficient condition. So the second order sufficient condition is stated in a slightly different way. Okay, there it is. Yeah, this is the second order sufficient condition. Suppose x star that is prime or feasible, and lambda star u star. Be careful here. This is nu and this is lambda in our notation. Okay, and this is our Kkt condition. This is complementary slackness. So we all satisfy our Kkt conditions, and then second order one is different. Here, this is same as our Hessian of the Lagrange function, Lagrangian, and this is strictly greater than 0. Okay, that's the difference, because our second order sufficient condition means that in that case it's a strict local minimizer, Now, for y, we slightly modify. Here, the difference is that before, in the necessary condition, we have used our index set. But the difference is that this is the kind of, let me show you how they differ. Now be careful, this is not exactly. Okay, let me be careful. Okay, so here we talk about y, okay, so I'd better say y like this. Yeah. And intersection I is I tilde of x star, and I will define this different index set. Here, I tilde of x star is the index of I such that, of course, this is active, but corresponding lambda star I is strictly positive. Okay, so this is different. Before, we just had this one, right? Activeness. But now we have strict positivity of corresponding Lagrange multiply. So, which one is bigger? I or I tilde? Since we have more constraint, I tilde is smaller. I tilde is contained. But when we talk about tangent space, if you have less number of constraints, this tangent space is bigger than this tangent space. Okay, got it? So be careful. Anyway, so this is done with our chapter 21 actually. There are many examples I just skipped like this. You work on it. Got it? So you try to solve every example at least on our lecture note. Okay? At least. And also some homework problems our TA has selected. We are going to probably, I and TA will work together to make up some exam problems that are not that far away from those examples on the lecture note and homework problems. Okay, now we don't have enough time, but I think 2 minutes is okay. So let me just finish this next chapter. So so far we studied very general constraint optimization problems, but not that general. Why? Because I've drawn like this. Constraint, this is set of all constraint optimization problems. And here is the set of convex optimization problems. And here is the constraint optimization problems with functional constraints. What does that mean? As we just examined, the explicit constraint set is described by what? Equality constraint functions and inequality constraint functions. So we studied this part. And this chapter is entitled Convex Optimization and talks about entire this one. But be careful. As I told you, Stephen Boy's convex optimization does not talk about all of this. They talk about very specialized one. With so this is Stephen Boy's convex optimization problems where h of x, the equality constraint functions, looks like this. Got it? Oh, fine. But anyway, our textbook, Chong and Jack's book, talks about this one in general. And the most important property for that one, okay, is this one. A local minimizer is a global minimizer. This is very, very interesting property. Okay? As far as your optimization problem is convex, then if you find a local minimizer, then it's global minimizer. Very interesting. This statement is not satisfied in general for some problems outside this set. Got it? Another one is this one. Another important and you must remember is that some F, O, and C. First of necessary conditions are sufficient. What does that mean? The first of the necessary conditions were like this. If X star is a local minimizer, then blah, blah, blah. What does that mean? That is a way to find the local minimizer. Now let's combine with that one. What does that mean? If X star satisfies F, O, and C, it's a global minimizer. And so these F, O, and C's are something like this, as we've already seen long ago. For all feasible D, you still remember this condition? We derived, right? And if it's an interior, for all interior X, and of course third one is the Kkt conditions. Okay. So we can either use that one, either use that one, either use that one. And what can you claim for this problem? It's a global minimizer. Okay. So as far as you can show that first, or you can verify that the problem is a convex optimization problem, it has very nice property. That's why here in the Chong's textbook, only one chapter is dedicated to the convex optimizations, but now entire book is dedicated to convex optimization theory because of this so powerful result. Got it? So if I have a chance, I want to offer this convex optimization theory course, possibly next year spring. But I'm not sure. Everything may change. Okay? Anyway, what I believe is that is this. If you have studied very hard in this course, then if you watch that Stephen Boy's video lecture, of course the entire textbook and lecture note is available from the web. Of course you will have some difficulty because the pace is very fast. Okay? It's like my entire class maybe fit in just the first 1 month in his pace. Okay? It's very, very fast. But anyway, you can have a lot of lessons understanding of convex optimization. Okay? That's what I believe. Anyway, so if you cannot wait, just study. For example, during the summer. And anyway, so these powerful convex optimization problems must be stated, the definition. First, I believe you remember this. The in convex optimization problem, so this looks like you minimize a convex function defined on the convex set. Okay. Actually, precisely speaking, omega E intersection omega I is convex. Okay. But by saying that the convex function or a convex domain is actually tautology, which means that redundant. Because whenever you claim that a function is convex, domain must be a convex set. But I repeatedly said that the in general convex optimization problem, your objective function is a convex function, and your constraint set is a convex set, is that I wanted to emphasize the fact that you must have convex constraint set. Okay? So this is a general case. And your definition of convexity is stated in the textbook. I'm not going to talk too much about the convex optimization in this course and also in the exam. Okay? But you try to solve some problems in the homework. Got it? Anyway, your in-depth study must be deferred to that course or to your study for convex optimization. Got it? So just remember this interesting result. Okay? Then I may say in the problem like this, find the global minimizer of this convex optimization problem. So I may just let you circumvent proving the problem is convex. Got it? Because I'm saying that this is a convex problem. So you solve it. In that case, you can do that, right? By applying these first law necessary conditions. So, okay, I think I'm done. Okay. You read the lecture note, and anyway, try to understand as many part as possible. So we now have only one class meeting remained, okay? And as I have updated, okay, I'm going to talk about many topics, some miscellaneous topics. By the way, I updated this last PDF file, so please download the new one and bring this Wednesday. I'm going to talk about multi-objective optimization problems because it's important to understand some ideas in information theory. And some of you are going to take it probably next semester. And also I will talk about one discrete optimization problem, integer linear programming. And I will also talk about variational problems because if you are measuring in control, then this part is related to so-called optimal control, where our decision variable is not a vector, but a function. Okay? I will give you some examples, and then I'll wrap up the entire lecture. So we have only one class meeting left. That's all for today.